Good morning, everyone, and welcome back. We have come a long way together through this particular topic of viscous flow in pipes. We started with the fundamental characteristics of pipe flow, laminar versus turbulent, entrance regions, the fully developed flow. We derived exact solutions for the laminar flow. We explored the chaotic world of turbulence with its Reynolds stresses and viscous sublayer. We use dimensional analysis to create practical tools, the friction factor, the Moody chart, and minor loss coefficients. And last time we put it together to solve the real world problems involving single pipes and complex multiple pipe systems. So we now know how to predict what will happen in a pipe. If I tell you the pipe size, the fluid, and the pressure, you can calculate the flow rate. If I tell you the flow rate, you can calculate the pressure drop too. So, but here is the practical question. What if you don't have the luxury of calculating? What if you have an existing system, a water pipe in your house, a chemical line in the plant, a fuel line in an aircraft, or and you need to know right now how much fluid is actually flowing. So you can't calculate it without knowing the pressure drop, and maybe you can't access the pressure taps. You need to measure it directly. That is our topic for today, which is the pipe flow measurement. So we are going to look at two broad categories of devices. First, the pipe flow rate meters. These measure the instantaneous rate of flow, usually in gallons per minute or cubic meters per second. Second, the volume flow meters. These measure the total volume of fluid that has passed, like the odometer on your car, telling you how many gallons you have used. And here is the beautiful connection to everything we have learned up till now. Almost all of these devices rely on the principle we have already studied, the energy equation, the Bernoulli principle, and yes, we can even the head losses we have worked so hard to understand. So part one is the pipe flow rate meters, the obstruction type. Let us start with the most common family of the flow rate meters, the three classical devices, the orifice meter, the nozzle meter, and the Venturi meter. They are all based on a simple, elegant idea that we first encountered way back in the topic high velocity gas, high velocity gives low pressure. So the core principle of them is that if we look at this particular figure, you have a pipe with a flow somewhere along its length. You deliberately install a restriction. You make the area smaller. Now what happens? To get the same mass flow through the smaller area, the velocity must increase. And from the Bernoulli equation, which we studied as the inviscid form of the energy equation, and an increase in the velocity means a decrease in the pressure. So by measuring the pressure difference between the full pipe upstream and the narrowest point, the throat, you can infer the velocity and therefore the flow rate also. In an ideal frictionless world, this relationship is clean and exact. But here is where our topic comes in. We are no longer in an ideal frictionless world. We now understand viscous effects. We understand the head losses, and in these meters there are several non-ideal effects that account for. First, the flow does not always follow the geometry perfectly. In an orifice meter, the fluid has to make a sharp turn and it separates from the wall, creating a vena contracta, a point where the flow area is actually smaller than the hole you drilled. Secondly, there is always some head loss due to turbulence and friction. You cannot calculate these effects from theory alone. So what do? We used some same philosophy we used for the friction factor. We define a discharge coefficient over here, typically denoted as the letter C, capital letter C, with a subscript for meter type. This coefficient is determined experimentally and accounts for all the real-world effects, the vena contracta, the head loss, and the non-ideal velocity profile. So the actual flow rate is the coefficient times the ideal flow rate you would calculate from the Bernoulli equation. Now coming towards the orifice meter, let us start with the simplest and the cheapest orifice meter as shown over here. It is literally a flat plate with a hole in it sandwiched between two pipe flanges. That's it. It's inexpensive and easy to install and widely being used. So, but it has drawbacks in it because the flow has to make that sharp contraction and then sudden expansion. There is significant turbulence and head loss in it. The vena contracta forms just downstream of the plate, and the pressure tap at that point measures a very low pressure. The discharge coefficient for an orifice meter, denoted here as C subscript O, O for the orifice meter, is quite sensitive to the details of the construction, where the pressure taps are placed, whether the edge of the hole is sharp or beveled. This particular figure also shows the typical values of the C naught, and you can see it varies with both the diameter ratio beta, uh, where beta is the ratio of the hole diameter to the pipe diameter and the Reynolds number. So for precise work, there are strict standards for how these meters must be built. The second one is the nozzle meter, and as shown over here in this particular figure, instead of a flat plate, you have a contoured nozzle-shaped construction. This is more expensive to manufacture than a simple orifice plate, but it has advantages. The contoured shape guides the flow more smoothly. There is much less separation, and the vena contracta effect is greatly reduced. The flow is closer to ideal. As a result, the discharge coefficient for a nozzle meter, which is abbreviated as CN, is higher than that of an orifice meter. You can see this in this particular figure. The values of Cn are closer to 1, meaning less energy is lost. The nozzle meter is more efficient. Then the third one is the Venturi meter. Finally, we have the most precise and the most expensive of the three, the Venturi meter, as shown in this particular figure, named after the Italian scientist G.B. Venturi. So the Venturi meter is designed with one goal in mind, to minimize the head loss. Look at its shape. It has a smoothly contoured contraction section, which eliminates the separation before the throat. But more importantly, it has long, gradually expanding section downstream of the throat called the diffuser. This gradual expansion allows the fluid to decelerate efficiently, converting most of the kinetic energy back into the pressure, just like the ideal Bernoulli equation predicts. So, most of the head loss in a well-designed Venturi meter is due to the friction losses along the walls, not to separated flows and inefficient mixing. This makes it the most accurate and the most energy efficient of the three meters. So the discharge coefficient for a Venturi meter CV is very close to 1, typically between 0.98 and 0.99 as shown in this particular figure. However, this performance comes at a cost. The Venturi meter is larger, heavier, and more expensive to manufacture than the Orifice or nozzle meter. So you see a pattern here. You have three devices, all based on the same principle, but they represent a classic engineering trade-off. The Orifice meter is cheap and simple, but it has a high head loss and lower accuracy. Nozzle meter, on the other hand, is a middle ground, better performance and moderate cost, but the Venturi meter is the premium choice. High accuracy, minimal head loss, and higher cost and larger size. So which one you choose depend upon your application. If you are measuring flow in a laboratory where accuracy is paramount, you might choose a Venturi meter. If you are putting a meter in a plant where energy costs are a concern and you have the budget, a Venturi might pay off for itself in saved pumping costs. But if you are installing hundreds of meters in a water distribution system and energy loss is not critical, the cheap and simple Orifice might be the right choice. In example problem, a typical calculation for a nozzle meter, you are given the fluid, the flow rate, and the pressure drop, and you need to find out the required nozzle diameter. This is similar to the type 3 problems we discussed previously in the previous lecture. So it requires an iterative solution, but because the discharge coefficient depends on the diameter ratio and the Reynolds number, which depend on the unknown diameter. So this procedure is the same. Make a guess, check the chart, and iterate until you converge. Now, another other types of the flow meters, obstruction meters like orifices, nozzles, and venturies are not the only way to measure the flow rate. We have other common devices that use different physical principles like the rotameter, which is also called as a variable area meter. Now look at this figure. This device is called as a rotameter or a variable area meter. It's quite common in laboratories and industry because it's simple, inexpensive, and gives a direct visual reading. The rotameter consists of a tapered transparent tube mounted vertically with a smaller end at the bottom. Inside the tube is a small float. The fluid enters at the bottom and flows upward, pushing the float. As the float rises, the gap between the float and the tube wall uh, gets larger because the tube is tapered. The float reaches an equilibrium height where the forces on it are balanced and the weight of the float pulls it down. The buoyancy force pushes it up, and the drag force from the fluid flowing past it pushes it up. At equilibrium, these forces sum up to zero. The key is that the drag force depends on the velocity of the fluid in the annular gap around the float. For a higher flow rate, the float must rise to a position where the larger gap reduces the velocity enough to balance the forces. So height of the float is directly related to the flow rate. The tube is calibrated with a scale, so you can read the flow rate directly by looking at where the float sits. The rotameter is simple, has no external power requirements, and gives a continuous reading. It's not as accurate as the precision Venturi, but has many applications. It's more than sufficient. Another type is the turbine meter. Another common device is the turbine meter as shown over here. Inside the pipe, there is a simple freely rotating propeller or a turbine similar to a fan. As the fluid flows through the meter, it strikes the blade and causes the turbine to spin. The angular velocity of the turbine is to a good approximation proportional to the average velocity of the fluid. Faster flow means faster spinning. The rotation is detected magnetically. A pickup coil senses the passing of the blades and generates a pulse. By counting the pulses per second, you get the flow rate. By counting the total number of pulses, you get the total volume. So the turbine meters are very accurate over a wide range of flow rates and are commonly used for things like fuel dispensing and custody transfer applications where you are buying and selling the fluid. Now, part two of our topic is the volume flow meters. Now, let us shift our focus. Sometimes you don't need the to know the rate of the flow at this instant. Sometimes you need to know the total amount of the fluid that has passed and how many gallons of the water did my house use this month. How many gallons of gasoline did I just pump into my car? This is where the volume flow meters comes in. These devices measure volume directly, like an odometer rather than a flow rate. They are positive displacement meters. They physically separate the fluid into discrete volumes and count them. Number one of such kind of a meter is the nutating disk meter. The first example um, is of the nutating disk meter as shown in this figure. This is the device in almost every domestic water meter. If you have city water, there is probably one in your basement or at the curb. Here is how it works as described earlier. Inside a spherical chamber, there is a movable disk. This disk is mounted on a central sphere and is constrained so that it's always at an angle. It's not perpendicular to the flow. A fixed partition called a diaphragm divides the chamber. As water enters the chamber, it flows into one side of the disk, pushing it. Because of the disk's angled orientation, it cannot just rotate. It has to nutate. Nutation is a wobbling motion, like a spinning coin just before it falls flat. Just like that, the disk wobbles around the chamber, and as it does, it alternatively traps the water on one side and then the another. For every complete wobble, a precisely fixed volume of water is swept through the chamber and out the exit. A pin attached to the disc connects to a gear train that drives the dials you see on the outside of the meter. So by counting the number of wobbles, you measure the total volume of the water that has passed. The beautiful thing about this meter is its simplicity, as we already seen in this figure that it contains only one essential moving part, which is a disk. It's reliable, accurate, and inexpensive to manufacture. Now, the another type of meter is the bellows meter. As shown in this particular slide, this is the device on the side of your house that measures the natural gas consumption. It is more complex, it has more complex mechanism, but it operates on same positive displacement principle. Inside the meter, there are two flexible bellows, like accordion falls. A set of the valves direct the flow of gas alternatively into and out of these bellows. Now look at this sequence in this accompanying figure. In the part A, one bellow is filling, the other is emptying. In part B, the valves switch and the process reverses. In part C and D, the cycle continues. So for each complete cycle of the bellows filling and emptying, a known volume of gas passes through the meter. Linkages connect the bellows to the dials on the outside, giving you a reading of the total volume used. So it is a fascinating comparison between the nutating disk meter and the bellows meter. So one is an example of extreme simplicity, and one cleverly designed moving part. The other is relatively complex with many moving interconnected parts. So why this is the difference in between the two? It is dictated by the application actually. The nutating disk meter handles a safe, relatively high pressure liquid water. The bellows meter handles a dangerous low pressure gas, which is the natural gas. The gas meter must be sealed to prevent the leaks, and the bellows mechanism allows this. Each device is perfectly designed for its specific job. So let us wrap up today's discussion and indeed wrap up whole this topic about the viscous flow in pipes. So for measuring flow rate, we have devices like Orifice, Nozzle, and Venturi meters, which use the principle of pressure drop across a restriction. They require experimentally determined discharge coefficients to account for the real-world viscous effects we have studied throughout this chapter. We also saw other devices like the rotameter, which gives a direct visual reading, and a turbine meter also, which uses a spinning rotor. Secondly, for measuring the total volume, we have positive displacement meters like nutating disk meter for water and bellows meter for gases. These physically separate the fluid into known volumes and count them. So this brings us to the end of this particular course about the viscous flow in pipes. We have covered an immense amount of the material. We started with the fundamental question of how fluids behave in the pipes, and we ended up with the practical tools to design the systems and measure their performances. The concepts we have learned, the Reynolds number, friction factor, head loss, and minor losses, are not just academic exercises, but they are everyday tools of engineers who design the water supply systems, oil pipelines, ventilation ducts, and gas lines that are our modern world that our modern world depends upon. So thank you for your attention throughout this engaging topic. I encourage you to practice these concepts, particularly the example problems that in the previous few lectures I focused on. So the more you work with them, the more intuitive they become. So that's all for this lecture. See you next time in next course. Thank you.